This video is going to give an overview of working with polynomials. And we're going to start by considering power functions. A power function is of the form f of x equals a constant times x to a power. So something like y equals x squared is a power function. We've considered our quadratic functions in the past, and y equals x squared looks like a parabola. Goes through the origin, 1, 1, negative 1, 1. As you go to the right, it goes up. As you go to the left, the graph also goes up. It turns out if you graph y equals x to the fourth, it looks pretty similar. Also goes through the origin, 1, 1, negative 1, 1. Except the middle of the graph is a little bit flatter, and the ends go up a little bit more steeply. That's because if you raise something to the fourth power, it increases at a more rapid rate. Y equals x to the third is also a power function. This is one of our toolkit functions. Goes through the origin, 1, 1, negative 1, negative 1. Y equals x to the third has a graph where the right side goes up and the left side goes down. If you graph a function like y equals x to the fifth, or something with an odd power, the graph also looks similar. Except, just like when we looked at x squared compared with x to the fourth, as we increase that exponent, the middle of the graph looks a little bit more squashed, and the ends go up more steeply. If you raise something to the fifth power, it grows more rapidly than raising it to the third power. So let's summarize what we've learned with a table. We can summarize the end behavior, so what happens at the ends of a graph if we have a power function. We just saw that if we have an even power, like x squared or x to the fourth, both ends go up. But if we have an odd power, like x to the third or x to the fifth, the right side goes up and the left side goes down. If we put a negative constant in front of that power function, if we multiply that power function by a negative number, that reflects the graph over the x-axis, flips it upside down. So if we have an even exponent, like x squared or x to the fourth, but a negative constant, then both ends will go down. We learned in the past that when we have a quadratic function with a negative number in front of the x squared, the graph opens down. So the same is true if we have an odd power, but a negative constant, the graph is reflected or flipped upside down. That means the right side goes down and the left side goes up. We can describe this end behavior using a specific kind of notation. So for our even power, positive constant, both ends go up. Mathematically, I would say as x goes to positive or negative infinity, so that means as I go to the right or the left of the graph, the y values go up. The y values go to positive infinity. In the case of the odd power, positive constant, as x goes to infinity, that means as we go to the right, the y values go to infinity. The graph goes up. But as we go to the left, as x goes to negative infinity, the y values go down or go to negative infinity. So my other two cases, even power, negative constant, both ends go down. I would describe that as x goes to plus or minus infinity. That means when I go to the left or the right, the y values go down. The y values go to negative infinity. And then finally, odd power, negative coefficient. As x goes to positive infinity, that means as we go to the right, the y values go down. F of x goes to negative infinity. As we go to the left, on the left side of the graph, as x goes to negative infinity, the y values go up, or f of x goes to positive infinity. So let's see how this works with some examples. Describe the end behavior of each function. So in general, if you have a polynomial, the end behavior is determined by the leading coefficient. And the leading coefficient of a polynomial is the term with the largest exponent. The largest exponent dominates what happens when x is really, really large. So for example, if I have the polynomial f of x equals 2x to the fourth minus 3x plus 7, the leading term is the 2x to the fourth. That's the largest power of x. I have a positive coefficient and an even exponent. So that means both ends go up. So if I were to graph this function, I don't know what happens in the middle right now, but I know that as x goes to plus or minus infinity, if I go to the left or the right of the graph, f of x goes to positive infinity. The y values go up. In my second example, we have the function f of x equals 5 minus x plus 3x squared minus x to the fifth. The leading coefficient is the largest power of x. Negative x to the fifth is an odd exponent with a negative coefficient. So that means the left side goes up and the right side goes down. Or we could say, as x goes to positive infinity, as we go to the right, the graph goes down. The y values go to negative infinity. As we go to the left, as x goes to negative infinity, the y values go up, or the y values go to positive infinity. So again, we can determine the end behavior of a graph of a polynomial by looking at the term with the largest exponent. The second piece of information we're going to want to know about polynomials is the intercepts. Where does the graph cross the x-axis and the y-axis? So let's take a look at a couple of examples. If I have the function f of x equals 2x times x plus 5 times x minus 3 squared, what are the intercepts? Well, to find the y-intercept, we're just going to plug in 0 for x. If I replace all the x's with zeros, I get 2 times 0 plus 5, which is 5. 0 minus 3 is minus 3 squared. If I multiply all of this together, I get 0. So when x is 0, y is 0. That tells me that the graph goes through the origin, or the point 0, 0. If I want to find the x-intercepts, I have to set y, or f of x, equal to 0. So if I put 0 in for the f of x, I get 0 equals 2x, x plus 5, x minus 3 squared. This polynomial is already in factored form, so I can set each of the factors equal to 0 and solve. If 2x equals 0, x equals 0. If x plus 5 equals 0, x equals negative 5. If x minus 3 equals 0, x equals 3. So I have x-intercepts at negative 5, and 3. Or as ordered pairs, intercepts at the point 0, 0, negative 5, 0, and 3, 0. Here's another example. Let's see if we can find the intercepts of the polynomial p of x equals x to the fourth minus 6x squared plus 9. To find the y-intercept, we need to plug in 0 for x. If I put 0 in for both of the x's, I get p of 0, or y, equals 9. So I have a y-intercept at 9. To find my x-intercepts, I have to plug 0 in for y, or in this case, p of x. So I put 0 in for the output, and I get 0 equals x to the fourth minus 6x squared plus 9. This polynomial is not in factored form, but this is a quadratic type function, and we can factor it. To get a product of x to the fourth, I need an x squared times x squared. To get a product of 9, it has to be 3 times 3, And I need both of those to be negative to add up to a negative 6 in the middle. So I have factors of x squared minus 3, x squared minus 3. If I set my factors equal to 0, x squared minus 3 equals 0, I can add 3, so x squared equals 3, and then take the square root, don't forget the plus or minus, so x equals plus or minus root 3. So I have two x-intercepts, one at positive root 3, one at negative root 3, and one y-intercept at y equals 9. Here's another example. Let's see if we can work backwards now. Write the equation of a polynomial with zeros at x equal 2, x equal negative 1, and x equal 3. So first of all, this word zeros means x-intercepts. Zeros are the exact same thing as x-intercepts. So if they're telling me what numbers are x-intercepts, then just thinking about the previous problems, if we know we have a 0 at x equal a, then x minus a has to be a factor. Because to find x-intercepts, we factor the polynomial and then set the factors to 0. So that means in this case, if x equal 2 is a 0, x minus 2 has to be a factor. That's where that solution came from. If x equal negative 1 is a 0, that had to come from x plus 1. So we're just working backwards, thinking about where those solutions come from. If x equal 3 is a 0, x minus 3 has to be a factor. So the product of those three factors would be my polynomial. So the next thing I'd like to define is the idea of multiplicities. So let's find the zeros and state their multiplicities. And I'd like to apologize for the background noise. My dog is very anxious with polynomials and needs to play with a squeaky toy right now. So find the zeros. That means, again, zeros are x-intercepts. And the new part is state their multiplicities. So multiplicities of a 0 is the number of factors that give that 0. How many times do you get that solution or that x-intercept? And so this will be easiest for me to explain with an example. So let's consider the function f of x equals x plus 1 squared times x minus 2. To find the zeros or the x-intercepts, we plug in 0 for y. This polynomial is already in factored form, so we can set x plus 1 equal to 0, and we get x equal negative 1. Now, because that solution came from an x plus 1 squared, technically there are two factors that are giving us that x plus 1, or that solution of x equal negative 1. So we say x equal negative 1 is a 0, but it has a multiplicity of 2 because it comes from two identical factors. Or in other words, the exponent with that factor is a 2. The other factor is x minus 2. That gives us a 0 of x equal 2. That factor technically has an exponent of 1. It only occurs one time. So we say that 0 has a multiplicity of 1. Now, why do we care about multiplicities? They give us information about the graph of the polynomial. So I put into a computer this function y equals x plus 1 squared times x minus 2. And I have on the screen what the computer generated for me. So I'd like you to notice that at x equal negative 1, that's an x-intercept, or 0 of the function. Notice that the graph just touches at x equal negative 1. But at x equal 2, which is also 0 of the function, or an x-intercept, the graph actually crosses the x-intercept. It turns out, anytime you have a 0 with an even multiplicity, like multiplicity of 2, the graph is just going to touch the axes. But if you have an odd multiplicity, like 1, the graph is going to cross the axes. So multiplicities of zeros give us more information about the graph of these polynomials. And so let's use that information just to create a rough sketch of the graph of each polynomial. So we are going to create our graph, we're going to determine the end behavior, we're going to find the zeros, and we're going to think about their multiplicities. So let's put together everything we've learned into this video to create a picture that goes with the polynomial shown. So we'll start with f of x equals 2x to the fourth minus 4x to the third. To find the end behavior, I look at the leading term, largest exponent, so 2x to the fourth. I've got a positive coefficient, an even power. That means both ends go up. As x goes to plus or minus infinity, y goes to infinity. So both ends go up. Next, to find the zeros, I'm going to set y equal to 0, and I'm going to try to solve by factoring. In this case, I have a greatest common factor. I can pull out a 2, and I can also pull out an x to the third. Then I'm left with x minus 2. If I set each of these factors equal to 0, 2x to the third equals 0 gives me x equals 0. X minus 2 equals 0 gives me x equals 2. X equals 0 has a multiplicity of 3 because it came from an x to the third. An odd multiplicity means the graph will cross the axes. X equals 2 has a multiplicity of 1. That's another odd multiplicity. The graph will cross the axes. So based on this information, I can create a crude sketch of this polynomial. It's not going to be perfect, but I know that this polynomial has x-intercepts or zeros at x equals 0 and x equals 2. I also know the end behavior. Both ends go up. So going from those intercepts, I can draw arrows on the right that goes up, an arrow on the left that goes up. Finally, I know at x equals 0 the graph crosses, and then it crosses again at 2. This isn't a perfect graph. I don't really know what happens in the middle of the graph, but I have enough information to draw the end behavior and the behavior at those zeros. All right, let's do another example. We've got the function f of x equals negative 2, x minus 3 squared, x plus 1. So for the end behavior, if I were to multiply all this out or FOIL all of this out, we have a negative 2, we'll have an x squared, and an x. That means our leading coefficient, our leading term, will be negative 2, x to the third. That's the x squared times x, gives me x to the third. So we've got an odd exponent and a negative coefficient. That means the right side goes down and the left side goes up. Or, as x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. I can also find the zeros by setting the factors equal to 0. X minus 3 equals 0 when x is 3, and x plus 1 equals 0 when x is negative 1. X equals 3 has a multiplicity of 2 because we have that exponent of 2. There's technically 2 factors of x minus 3. X equals negative 1 has a multiplicity of 1 because that's only one factor. Even multiplicities mean the graph touches. Odd multiplicities mean the graph crosses. So here's my rough sketch. I know the graph has x-intercepts at negative 1 and 3. Those are the zeros of the graph. I know the end behavior. The left side goes up and the right side goes down. I can finish my picture by using information from my multiplicities. I know at negative 1, the graph is going to cross, and at positive 3, the graph is just going to touch the axes. So I'll draw something that crosses at negative 1, but just bounces off or touches at positive 3. That was my last example in this video. We're going to continue to expand on this topic in the next couple of sections. But as always, please let me know if anything from this video is unclear.